Hello and welcome to part 5 of the video series on vector analysis. The topic of this video is vector integration, which is crucial for understanding and quantifying how vector fields interact with curves, surfaces, and volumes. Vector integration allows us to calculate important physical quantities such as work done by a force field using line integrals, flux through a surface using surface integrals, and the accumulation of a quantity within a volume using volume integrals. These concepts are fundamental in physics, engineering, and other fields for analyzing fluid flow, electromagnetic fields, and many other vector-driven phenomena. Let's look at an example of line integrals. As I said before, we use these to find the work done in moving an object along a path against a variable force. In the current example, the vector field is specified by 3x squared plus 6y I hat minus 14 yz j hat plus 20xz square k hat. And we want to evaluate the line integral along the straight line joining the points 0, 0, 0 and 1, 1, 1. In other words, we want to find the work done by the variable force along a space curve, which in this case is a straight line. This is the code we use to make this figure on the right hand side. We create the mesh grid using the x, y, z vectors and then compute the function value which returns a vector for each spatial point. Then, for better display of the vector field, we normalize the vectors at each point by their corresponding magnitudes, and we scale these vectors appropriately. Finally, we use the quiver method to plot the vector field. And this is the main code for the figure on the right hand side, where we are plotting both the vector fields and the vector in 3D, showing the motion of an object along the space curve. Now, to solve the problem, we first find the parametric representation such that the motion along a curve in terms of the parameter t is written as a vector rt. And since this curve is a straight line, RT is equal to Ti hat plus Tj hat plus Tk hat, where T is defined in the interval between 0 and 1. The work done can then be written as the line integral, where dr by dt, if we recall from the previous videos in this series, is the tangent to the curve, or it represents the direction of motion along the curve. The dot product between f and dr by dt then represents the component of force in the direction of motion, which can be solved in terms of t, and when we take the integration between 0 and 1, the total work done by the force field as the object moves along the curve is 13 by 3, which is a positive number indicating that the force is aiding the motion along the curve. Let's now look at an example of surface integrals. Here we want to find the flux of f, which in this case is yz j hat plus z squared k hat outward through the surface cut from the cylinder y squared plus z squared equal to 1 for z greater than or equal to 0 by the planes x is equal to 0 and x is equal to 1. If you don't know what flux is, it's a measure of how much of a field passes through a surface, and it is used extensively in physics to analyze and simplify complex systems, especially in electromagnetism and fluid dynamics. This is the code we use to generate this figure on the right hand side. We first define the x, y, and z and plot the vector field as explained in the previous slide. The vector field function is updated here for this problem. Then we plot the surface using plot underscore surface method from the matplotlib library. Now let's calculate the flux of the vector field across the oriented surface, which can be written as a surface integral where n is the unit normal to the level surface, and we know from the previous videos of this series that gradient of a level surface, which is g in this case, is normal to the surface at any given point. D sigma here is the surface area differential, and P is a unit vector normal to the shadow region of the level surface. The gradient of the level surface y squared plus z squared equal to 1 is equal to 2yj hat plus 2zk hat, and the magnitude of the gradient is equal to 2. The outward normal field on the surface S is then equal to yj hat plus zk hat. Since the shadow region for this surface is in the xy plane, the normal to this plane is k hat. Therefore, p unit vector is equal to k hat. The d sigma can then be reduced to 1 over z dA. Now the dot product between the vector field and the normal field is equal to y squared z plus z cubed, which again, using the definition of the level surface, can be reduced to z. Finally, the flux value for this problem is reduced to area of the shaded region, which, knowing that x varies from 0 to 1 and y from -1 to 1, is equal to 2, which is a positive value and which indicates that there is a net outward flow of the vector field through the surface. Now let's look at an example of volume integral. Here we have a vector field f, which is 2xz I hat minus xj hat plus y squared k hat, and we want to find the total amount of the vector field within a region which is a volume bounded by the surfaces x is equal to 0, y is equal to 0, y is equal to 6, z is equal to 4, and z is equal to x squared. We can plot the figure on the right hand side using this code. Like before, we define the xyz dimensions and plot the vector field. Then we create the mesh grid and define the surfaces and plot these using the plot underscore surface method from matplotlib. Now we can write the volume integral, where we first keep x and y fixed and integrate over z, then keeping x fixed we integrate over y, and finally we integrate over x. The result of this integral is equal to 128 I hat minus 24 j hat plus 384 k hat, which shows the net effect of the vector field f within the given volume. Physically, this vector could describe a total force, momentum, or flow direction depending on the context of the vector field. With this, we conclude our video. In the next video, we'll learn about some important integral theorems. I hope you liked this video. Please subscribe to my channel for more videos like this. Thanks for watching and see you in the next video.